see. Good morning, everybody. Okay. So let's take a look here at where we're at and what we're doing. I hope you guys are doing okay. I hope you guys are awake. We're working again on these improper integrals, and so we're gonna do a few things here. So let's actually go to our browser, and in the browser, we're gonna recall a few things here. Okay, so let's see. Let me get coordinated here. Alrighty. In our browser, we're going to go to our course. And let's double check down here to the lower right. Okay. And let's see if you guys can actually see that. There we go, to the lower right. What you guys can see is your test 2 take-home portion. There's about 10 questions here that, I wanted to make sure you guys work on to try to see if you can answer. They should be familiar to you. And, of course, this is going to be due Monday. So Monday is going to be, let's check our calendar. Today's Thursday, the 16th. So let's see, Monday is going to be the 20th, April 20th. So remember, this is going to be due before class, April 20th. All right, Monday, April 20th, this is due before class. So this is the take-home portion for you guys. And that'll be 25 points. Combined with your in-class, it's 125 for the in-class. So total is 150. Anyway, here's some problems you guys can work on as well. Okay, so it's on my website like I promised you guys yesterday. Lower corner here, we're at the bottom, and that's where you're going to find it. Also, let's think about some more things here. I think that's pretty much it for us this morning. Anyway, okay, so let's go and let's think about here what we're doing. And let's get our gear up and running. And let's find here 262. We're looking at improper integrals. Okay. So let me actually do something here. Let's go to our iPad. And yeah, I actually already did it. It was already there. So here's where we're at. We were looking at first the type 1 improper integrals. These were infinite intervals, as you guys can see there. And now we're going to, and they had 3 cases. And I'm going to here, the type 2, that we have discontinuity. Well, let's just say this. We have here for type 2, points in the interval where the function is discontinuous. And we call that infinite discontinuities. So we're going to do, these type 2s now, infinite discontinuities, and let's kind of write this down here so you guys know. Let's just give you the general idea that you have here an integral now from a to b. Here's your function, dx. And of course, this interval is a closed interval from a to b. This is how it's different. Okay, it is no longer going to be an endpoint that is infinite or not, or minus infinity, right? Positive infinity or negative infinity at an endpoint. What's going to happen now, though, is you're going to have the function here. It's going to have a discontinuity. And it's going to be for some c in that interval. So there's a discontinuity here. This function is no longer continuous over the interval. There's a discontinuity. Okay? And so there's a lot of different good examples. So let me give you a basic idea of how this works here, right? So if I kind of look at an example, it's a classic example. 0 pi over 2 of secant. Let's do something like this. This will be an interesting kind of question here for us. Okay, so notice again we have a closed interval from A to B. Okay, just like we're describing up here. Closed interval. But then the question's going to be now here. Where in the interval do we have a discontinuity? Okay, so in this particular interval now, where do we have a discontinuity? And you say, what interval are we talking about? Since 0 to pi over 2. So here's a pretty good example. Okay, there's many that you can look at. So I want to point out to you guys a couple of things here. Let's do this. Let's go to our trusty. Oh, let's go over here. Okay. Let's find the functions here. Secant x. And I'm in actually here. Let's remove this. Get it out of the way. I'm actually in what is known as projector mode. So I can actually change that mode if you guys like. Maybe it's too much. I don't know. Maybe that's a little better. I don't know. Okay. Now, here's what I want to point out to you guys here. Let's take a closer look at what's going on here. Okay. Maybe you can see it. Maybe not. And I'm going to do something that I was not able to do yesterday. Oops. I guess I want to go to Device, More. Here's a screenshot. Okay, let's take a look at this here. I should have actually colored this a different color, but that's fine. It doesn't matter. We're going to look at something like this here, right? Remember, 0, x is 0 is around here. So let's kind of color this. Okay. This is where x is 0 would be, and then that's kind of a not so good, but anyway. Let's do something like this. This is where x is 0. Now that's a crayon. Let's not do crayon. Sorry about that. I guess it's my artist tendencies here, right? And let's be kind of thick. Okay. There we go. A lot better. Here's where x is 0. Now, we're looking at 0 to pi over 2. Pi over 2, pi is approximately 3, so divided by 2, it's about 1.5, a little more. Here's my point. We have here, when x is pi over 2, a vertical asymptote. Okay? So here's the point. We're going to try to find the area under this curve here. Now the area under that particular curve, don't want that. Let's change that if we can. Okay, here's the area under our curve we're looking for. Yikes. Okay. You guys get the picture. We have a discontinuity. We're looking for the area under that particular curve. Okay. Now, I don't think I want to save this photo. Anyway, you guys see the point. The question's going to be now. Let's not say, okay, let's, all right, well, let's save it maybe. Who cares? Here's our point. This function is discontinuous, right? Secant is discontinuous at x equals pi over 2. Okay, so here's the problem here. We have a discontinuity because there's a vertical asymptote at that point. So let's appreciate really what's happening here, ladies and gentlemen. I'm going to draw a quick little picture here. Okay. And we know that this curve is going up forever, starting at 1. And, of course, we had that vertical asymptote. Okay? So x will be pi over 2 here. And this is over the interval 0 to pi over 2. So here's my interval that we're going to try to integrate over. Okay, 0 to pi over 2. And then we have a problem here at pi over 2. So we're going to fix our problem. So here's where we're at. Let's take a look. We have case 1. So let's determine case 1. What does that say? The function f is continuous over the interval a to b and is discontinuous at the right endpoint b. So this is actually what we're talking about. So let's actually go back here in our picture and say this is what this means here. Your function is continuous on this interval. Okay? And that interval here is from 0 to pi over 2. The right endpoint is open. It doesn't include pi over 2. So it satisfies our condition. And this is what you're going to have. You're going to have a situation here where the function is going to be discontinuous at an endpoint. In this case, it's at the upper limit value of b. So it's discontinuous right here. Okay? So this is the situation. We're still trying to find the area under that curve. And we're still trying to determine whether or not that area is going to be either infinite or finite. Okay, so here's our task. Let's write that down. Is this area infinite or finite? So that's what we're trying to do. And this is a case 1 situation. Okay, and so for case 1, we notice here's how you fix the problem here, right? We're going to use the definition. So here's our definition. If we have to integrate from a to b, fx dx, in this case, the upper limit has a discontinuity. This is going to equal a limit. I'm going to replace that value with t. Okay, we replace it with the t. I have my function f dx. Now, be careful here. As you guys know, t is going to have to approach b. But t is going to approach b from what direction? If I go back to my graph to remind you, We just replaced the right endpoint with t, so that when we try to find this particular area, right, this I of t integral, t now has to approach b. So here is my t. Here is my b, really. So t gets close to b. We're going to let t approach b from the left, because you're approaching from the left here. And that's what you guys have to put. This is the definition. So this is case one, where what you have here is the right endpoint has the discontinuity. And we're going to approach, by letting t be the dummy variable, we're going to approach the b value from the left. And that's why you see in your definition, if the limit exists and is finite, we have convergence. Also, we have divergence. That's why you see a left approach for a limit value. So here's your definition. Here's what you guys are going to use. Okay. So there we go. Let's highlight this. It's also in your notes, so you guys know I put this in our notes. And so let's proceed here with how to answer this particular question, right? So we have the integral here from 0 to pi over 2 of secant. By this definition, we have the limit as t goes to pi over 2 from the left, the integral of 0 to t secant x dx. And as you guys remember here, your real work here is to evaluate this integral. That's where you start. And so, like I mentioned on your test, like I mentioned in the past, it's good to know some of these integrals, right? You should know what these are. So this is the natural log absolute value secant x plus tangent x. Of course, you have to evaluate this from x is 0 to x is t. Right? And this is the I of t we're talking about. So at this point, if we use the limit values, this becomes the natural log, because this is now going to be f of t, right, minus f of 0. So we have the natural log absolute value secant t minus tangent t minus natural log absolute value secant 0 minus tangent of 0. So we're going to need to know what some of these values are, right? Now, secant of 0, if you go back to the curve we looked at, kind of right here, right? Secant of 0 we know is 1. So this portion is 1. Tangent of 0 is 0. You can refer to the tangent curve, right? And moreover, on the right side here, this means we got the natural log absolute value of 1 minus 0, which is the natural log absolute value of 1, which is natural log of 1, which is 0. So this whole thing is actually gone. And what you're really left with here, ladies and gentlemen, is I of t is really the limit of secant t minus tangent t in absolute value. All right, is that plus, Marbella? Is this a plus? You guys remember? Integral secant, natural log secant plus tangent. Thank you. Good. All right, good. It's a little early for me, but okay. You guys have those integrals memorized. Thank you. That's a good observation. Now, here's the I of t now. What happens here now is you go back here and you say, what's the deal? We're going to have to evaluate here the limit as t goes to pi over 2 from the left. So here's what we're going to say. as t goes to pi over 2 from the left, I of t goes where? Okay, so we're going to have to look at this limit here. So here's our limit. We're going to say, what's that limit as t goes to pi over 2 from the left? Natural log absolute value of secant plus tangent. And that's going to be a very important detail. So since both of these curves here, take a look here. I'm going to have to find that limit. I'm going to have to find that limit. So we need to know, as t goes to pi over 2 from the left, where does secant go to? And where does tangent go to? If you guys recall. And this is pi over 2 from the left. Well, I have one answer, because if I go back to the original curve here, here's secant. If I get to pi over 2 from the left of this secant curve, here's my secant curve, remember? It's secant x, but it doesn't matter. The secant goes to infinity. And if anybody remembers about tangent, if you guys recall the tangent curve, tangent, this is pi over 2. Negative pi over 2. I don't like that. Sorry about that. Can the artist in me? Maybe it's something like this. It's closer to something like this here. We should have been a little bit more careful, but it doesn't matter. Here's your tangent curve, and if you go to pi over 2 again from the left side, right, and this is t, these points, the y-coordinate value also goes to infinity. So what you guys know here is you have a sum here. So if you have Oprah money and Bill Gates money, if I add infinity, right, plus infinity, that is a whole lot of money. Now, the absolute value, natural log, blah, 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 the natural log curve, as it gets big, we know, we say the natural log of secant now, plus tangent, is going to get big because the natural log curve. So here's what we know. This limit goes to infinity here. So since the component function secant plus tangent go to infinity, the natural log also goes to infinity because that curve is increasing. I'm not going to draw that natural log curve. You guys have seen it a lot of times here already. The point is you have divergence here. So this here equals infinity. We have divergence. And what that means here is that this area is actually infinite. Okay. Well, whatever, we'll just do it this way. So it blows up. There's too much area there. And what happens in this case is the curve just simply doesn't get to the asymptote fast enough, the vertical asymptote. And that's why it's going to be infinity here. So anyway, there's a situation where we have what's called a type, a case 1 for the type 2 improper integral where you have discontinuities in the integrand. Okay, so here's an example of how to use that definition. It's just a limit. We're going to look at case 2 now. Or we can even look at a case 1. Again, doesn't matter. But we're going to look at some of these functions here. Okay, how about if we do something like this here? Let's look at a case 2 example. 0 to 1, natural log x dx. These are all very, very good questions here. And if you guys remember, I think I'm going to draw my curves here this morning. I didn't really like how that came out with the graphing calculator there and trying to write on that. I don't think the tools are very good there. But let's kind of draw a natural log curve. Okay. X-axis, y-axis. You guys know this is going to be where 1 is. And we're getting close to the y-axis. What they're asking now here, since we have 0 to 1, our interval here in this picture is 0 to 1. So here's 0, here's 1. That's the interval, and they're going to say, what about this area here? Keep in mind the curve gets close to the y-axis. The question's going to be, is this area infinite, right, or finite? That's what we're trying to answer. So in this example, because you have on the y-axis at x equals 0 a vertical asymptote, I'm going to say to you, this portion you have a discontinuity right in here. Okay, so your function here is discontinuous here. Okay, and discontinuous at x is 0 here. All right. Now, let's take a look. All right. Here's the deal. Oops. And we're going to now have to approach. We're going to look at this here. This is going to be a continuous function, so you guys know technically we can say this function here now is going to be continuous from 0 to 1 if the right endpoint is open. And so to apply the definition, remember this is going to be the integral from 0 to 1. And let's go back. Let's actually write down that definition here for us. A to b, f of x dx. We're going to replace the bound with t. So we're going to have the limit as t goes to. Which bound do we have the discontinuity? It's going to be, in this case, the lower bound on the left. So replace this with t. The upper bound stays the same. It's going to be b. And so we're going to approach b now from the right in this example, so we know. So if we go back to our definition, sure enough, and it's actually a. It's an a. We're going to have t go to a because it's the lower bound, right? So let's go back. This lower bound here is where you have the discontinuity, and this is why we replace it with a t. So that means t has to go to the a here. And it's going from the right because t would really be over here. Here's that t value, and so now t has to get to this a value, and you're coming from the right side. So anyway, using this definition here, the integral 0 to 1 natural log x dx is the limit. Here's t, here's 1, natural log x dx, t goes to 0 from the right. Again, because we have a vertical asymptote for the lower limit value, and so we approach 0 from the right now. This is using the definition. At this point here, here's our I of t. So we're going to have to find that integral, I of t. T to 1, natural log x dx. Now, if you guys recall, you use IBP, integration by parts here. And what this gives us is x, natural log x minus x. And this is from our past. And of course, we evaluate this from t to 1. So this is going to be f of 1 minus f of t. So let's plug in our limits here. 1, natural log 1 minus 1 minus t, natural log t minus t. So we're going to get here 0. And what this ultimately means, let's double check to see if we did everything okay. We're going to get negative 1 minus t, natural log t, plus t. So double check to see if we did our algebra okay here. Okay, you guys okay with that algebra? Okay. I of t now, let me write this down. I think I'm going to write it, I get a little bit, mathematicians, we like our terms to start positive. So I'm just going to rearrange my terms here. Right, I'm going to start with a t, it's positive. I got minus t, natural log t, minus 1 now. So at this point, let's remember, we have to apply the limit right here. As t goes to 0 from the right now. So we're going to say, as t goes to 0 from the right, we want to know what I of t goes to. That's really the limit here. Let's do it this way. T goes to 0 from the right of t minus t, natural log t, minus 1. That's the limit question we have to answer. So at this point, ladies and gentlemen, let's use properties of limits. Right? This will be the limit as t goes to 0 from the right of t minus the limit t goes to 0 from the right, t natural log t minus the limit t goes to 0 from the right of 1. This is 0, and this is 1 because it's a constant. Let's get this out of the way. So the real question is going to be, what is this limit right here? Okay, and so we know from our past whatever work, remember your past is never too far behind you. Let's raise this mic. We're going to have 0 times negative infinity. Okay, so here's an example. 0 times negative infinity. Your past is never far behind. This is where we studied Lapidus Rule. Right? We call this an indeterminate product. So because of that, we have to fix the situation. Oops. Well, okay, whatever. All right. We got to fix this. Indeterminate product. So to evaluate that limit using Lapidus Rule, right? I'm going to say H here for Lapidus Rule, or before we even do that, we have to fix it. So let's do the fix. If you guys remember, keep one function the same, look at the reciprocal of the other. And this is now going to give us negative infinity, okay? And as you go to 0 from the right of 1 over t, that's positive infinity. So this is an improper quotient. Here's where we use Lapidus Rule. So by Lapidus Rule, that's going to be the limit. T goes to 0 from the right, 1 over t over minus 1 over t squared. And so doing your algebra here, 1 over t times minus t over squared, we just get negative t. So this is the limit as t goes to 0 from the right of minus t. You guys know where that goes to. It goes to 0. Is that right? All right. So let's go back and we say, oh, we know what this limit is by Lapidus Rule. And so the final answer here is going to be simply negative 1. That's the answer to the limit. And negative 1 now, we say, oh, so this goes to negative 1. We found that answer. That's the same answer. Which means, ladies and gentlemen, that this also equals negative 1. The original question here, this is negative 1. So we have here convergence. And moreover, if we erase all this, the area under this particular curve is negative 1. And that curve is kind of small, and I apologize for you guys here. If I had to do it all over again, I'd draw it really bigger. But that's a case 2 example. And this is how you handle this kind of improper integral. Okay, the lower bound is actually the point of discontinuity. And but the area under this curve got to the y-axis fast enough. So this here is what we're saying. This is the area under that curve. It's actually negative 1. It's finite. All right, pretty good. But this is a case 2. Now, I want to show you another famous example here of what happens where you have case 3. Now, notice what case 3 is. Here's going to be an example of case 3. Let's say negative 1 to 1, 1 over x squared dx. Be very careful here. My interval is between negative 1 and 1. Anyway, just checking a few things here. Okay. Now, if you guys remember, let me draw this picture. I'm going to draw a bigger picture this time. This is why this is a case 3. this curve looks something like this. Okay, and if you guys recall here, you got something happening at 0 here, right? This is where an x is 0, by the way, a vertical asymptote. And so the original question is, okay, if we go from -1 to +1, this is the interval they're talking about. I want to find the area. Under the curve over that interval. So you have a real situation here. Okay? What this is saying that your function is discontinuous for some number c in the interval AB that's given. This is why this is case number 3 here. So if I go back here and say case 3, the function has a discontinuity, okay, for some c in the interval that is not at an endpoint. And 0 is not at +1. 0 is not at -1. 0 is, it's actually right in the middle of the interval. Okay, sorry, I'm adjusting some things here. Okay. So what do we do in this case? Well, here's what you guys do. Right? You're going to create 2 improper integrals like you did yesterday. So in other words, what they want you to do is for some number in the middle, they want you to write a to b, fx dx as a at the discontinuity c, or at the vertical asymptote c to b. We have now 2 improper integrals. So there's now 2 improper integrals here, ladies and gentlemen. The discontinuity happens at the value c here. Okay. And so we split it up into 2, where we have case 1 and we have case 2 now. So it's discontinuous at some c here. In this example, it's going to happen at 0, because that's where we have our vertical asymptote. So we started the day. This was a case 1. This is a case 2 improper integral, and we're using, right, this definition. And we're going to have to now do double the work. Anyway, fixing this here again. All right. All right, that should help. Hopefully. Alrighty, here we go. So, to integrate from -1 to 1, 1 over x squared dx. This is now -1 to 0. 1 over x squared dx. 0 to 1. 1 over x squared dx. Okay, we got 2 to work on. So, I don't know which one you guys want to do first. Let's do the one on the left, I guess. Working left to right. So, -1 to 0, x to the -2 dx. Right, remember, the upper limit there is the asymptote. We replace that with a t. The lower limit stays the same. And don't forget, let's leave some space. Negative 1 to t, x to the minus 2 dx. The limit, x goes to t. Now, from what direction? How do we start the day with case 1? It's coming from the left. So remember, where you have the discontinuity, you replace that with the letter t. Okay? And then t here, let's rewrite this. You're going to say t goes to 0 from the left. I apologize. I'm focusing on this falling microphone. So distracting to me. I can't talk, write, think, and try to hold this mic up where it should be so that you guys can hear. Anyway, let me double check here, slow down and go, okay, this is the discontinuity at 0. Looks like we're good. And if you guys notice, I already wrote this in x to the minus 2 power here, right? In a way we can actually integrate nicely. This is the I of t. And so this becomes, add 1 to negative 2, negative 1 over x. From negative 1 to t. Right? Because this is going to be f of t minus f of negative 1. All right. Minus 1 over t minus negative 1 over 1, which gives you negative 1 over t plus 1, or 1 minus 1 over t. So now I take the limit here. And the limit here is t is going to 0 from the left. So here's what we're going to say. As t goes to 0 from the left, where does I of t go to? Limit. T goes to 0 from the left of 1 minus 1 over t. Properties of limits. Limit of 1 minus the limit of 1 over t. T goes to 0 from the left. So because we have a constant, here's my constant. The question is, where does that limit go to as t goes to 0 from the left? Okay, so let's double check everything here. Negative 1 to 0. All right, well, whatever. Okay, so does anybody know? Let's see, where would this limit go to? Let's double check here. Let's draw the curve. Is that minus infinity? And then minus the minus makes this really what? Positive infinity. So I have to think of 1 plus infinity in some sense, because this is 1 over here, minus a minus, well, this is infinite. In other words, we get infinity here for that limit. So you might say, oh, okay, then that means this answer here is infinity. It is. And of course, that means we have divergence. So if I know here we have divergence, the area blows up. That means this here is infinite. Okay. There's really no need to actually get the other limit. Okay, so this one we know here. Let's find it. We got divergence here for this first integral. We don't care about the next integral because, well, once you have divergence, the area blows up. There's no way you're going to actually recover that area here, okay? So here's the answer. This is divergent. Diverges again. And I want to let you guys know, if you wanted to find the other example here, you're going to probably get that to be infinite because there's some symmetry here. Do you guys know what we're talking about? That curve is symmetric about the y-axis or symmetric about the vertical asymptote. So this is an example of divergence for a case 3. But I want to remark here and give you guys here a note that additional examples this weekend. I'm going to post examples, and it's either going to be in PDF format or I'm going to do another video format here for examples of improper integrals for you guys. So I'm going to do that this weekend. So my chores here are going to be to make sure we get your test graded, the in-class version graded for you guys, and then make sure after that I get some additional examples for you guys, okay, of improper integrals. Both types, okay. First type, if you remember, first type, type 1, infinite intervals. I'm going to give you more examples. Type 2, you got a discontinuity at an endpoint or somewhere in the interval. So I'm going to do additional examples like I've done in the past for you guys. I'm going to upload them to the website and put them in Canvas. I apologize for not being able to hear me this morning. Am I focusing on playing with this mic? You know, I got a mic stand, and of course it lasts for 2 weeks and it breaks. And this is the frustration with the world right now. It's not just the obvious, but not everything works like it should. Only a couple of weeks, and then bam, you know, it hits you. So that's what's going on, playing with this ridiculous mic stand all morning long. So you guys are losing me in terms of audio and gaining me as I adjusted throughout the morning. I don't know. I'm going to have to try to figure out again what to do. Get another mic stand. I don't know. But again, if you guys have any additional questions, you guys can see me during office hours. And apologize for the quality this morning. But this is your improper integral lecture. I already gave you guys homework yesterday on it. So if you said, what was it? Well, go all the way back. Here was the improper integral homework. 8.8, 5 to 39 odd, do 57, 58, and 59. And like I said, I'm going to do some additional work for you guys this weekend, additional examples, and this will help fill in some of the gaps you guys may be experiencing, okay? So I want to thank you guys this morning. Having a bit of patience. Thank you for helping me out. And I will see you guys, what's today? Too many holidays? What's today? Thursday. I guess that means I see you guys on Monday. Don't forget, what's due on Monday is your take-home portion of test 2. So go back to the browser. Go back to find where that is. It's on 262. Your front page. Right down here. This will be due Monday right before class. Okay, so I'm going to set up this in Canvas. It's going to be in the announcement portion. Okay, I'm sorry, in the assignment portion of Canvas. And it's going to be obvious. Completed math 262 test 2 take home portion. And of course, you guys use your Canvas, your famous scanning app to upload it, your favorite one. Upload it. Please batch upload. Get that practice of scanning and uploading, because we're going to do this for the rest of the course. And we want to be efficient. And you want to send it into the right place, because when I grade, it has to go through the assignment portion. If you try to upload through quiz portions, that stuff doesn't allow you to use what's called speed grader. So I'll be grading your guys' exams today, tomorrow, blah, 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 this weekend. And you guys will see what I'm talking about. It's going to be uploaded in Canvas. You get the writing on it and everything. So anyway, stay safe. Have a good day. If there's any questions, come to office hours. If there's any issues getting in, email me because I get those emails and I'll let you in the door, whatever that is. It's kind of a big hassle. But, again, come see me and see how that goes. All right? So thank you guys. Have a great day and take care.